Today we're going to go through how to calculate different fundamentals for different sounds. So if we're looking here, so F deals with, just stands for fundamental, which fundamental are we finding? N stands for the number of fundamentals, and I'm going to go through that here in a second. But really we can have two systems of fundamentals. One is for a system that's opened. I'm talking about that here shortly. And then, of course, the opposite of opened, we're going to have a system for when our fundamental is for a closed system. So what is a fundamental? Kind of to kind of make it easy, is fundamentals really deal with at what frequency do we have standing waves forming. Okay, so what's a standing wave? So if I'm looking at like a guitar string or a slinky, essentially I can move that slinky back and forth to a point where it kind of looks like, so that's one end, that's the other, where it kind of looks like the slinky, let's see, if I move it fast enough, that's kind of a bad drawing, kind of looks like, yeah, that's super bad, let's redo that. We're going to give it a middle point. Maybe that'll help. I doubt it. I'm going to aim for that one, okay? Ooh, maybe that will help, okay? Pretend that hit there. Where it kind of looks like the slinky doesn't move at this point here, and it's just kind of moving back and forth here at the ends, okay? This is a standing wave, and you can see this, you can find videos of it, and really, when we're looking at like musical notes and stuff, is they're going to correspond to where these standing waves occur, because it's going to sound nice and pleasant. And we, in this case, if let's even grab the yellow here. Maybe. And let's bring that down to there. So now if I kind of follow, the one wave, it's kind of going about right there. We would say that's the first fundamental. Might help if I was actually using a real color. So that's the first fundamental. The second fundamental would correspond, and I'm pretty sure I got this right, we're essentially, just cut that off just to make it easier for me to, that's already kind of a wave, that's all right. Up, down, there. So those parts where we have, for parts of a standing wave, this part where it's not moving, that's called a node. And then here where it's moving the most, that's an antinode. So this right here where we kind of look like we have one, let's switch to a different color like this red, where we kind of can trace out two different waves. That would be the second fundamental. And you can have like steps in between. In fact, even the first fundamental is actually a half fundamental, which is weird to talk about because essentially it's just, it looks like the one wave, half of the wavelength goes there, and then when it gets reflected back, essentially that's, half a fundamental. Anyway, just kind of showing you what they look like. So for different instruments, this is the big place where we're actually going to see fundamental stuff like that, is in regards to musical instruments. So the open and closed part deals with kind of the end. With an open end, the wave is going to exit the instrument at that point. If you have a closed end, the wave is going to bounce off of that point. And so really the equations for these things are slightly different. So if I'm looking at the fundamental of an open instrument, that would be like a saxophone. A flute, I think, is the easiest one to talk about because it's just a straight pipe. It's opened pretty much at both ends. The formula we're going to use for this one is going to be equal to the number of whichever fundamental we're trying to find times the wave speed over 2 times the length of the, wherever we have this vibration taking place, wherever we have this wave in. If it's a flute, we're going to talk about the length of the flute. So N is just really just what fundamental are we looking for. Or if we're looking at like a closed thing, This would be like a guitar string where both ends of the string are kind of locked in place and the waves can kind of bounce back and forth in between there. The formula for the fundamental is just whatever fundamental we're looking for. Once again, times wave speed, but this time it's going to be over 4 times the length of, if it's a guitar string, the L. If it's a pipe organ, it's going to be how long the pipe is. All right, so typically, mess that up a little bit. Was that okay? No. Where's that? We're just going to do it this way. I'm trying to fix this. All right, so fundamental means kind of the first frequency, so we can just put a 1 in for n. So jumping right into this equation here in problem 14. So what is the fundamental frequency of a 0.2 meter long organ pipe that's closed at one end when the speed of sound in the pipe is 352 meters per second? All right, so fundamental frequency, that means our n is equal to 1. Fundamental first, kind of the first one is, we're just going to put n for 1. They give us that the length of the tubes are 0.2 meters. And the wave speed inside the pipe, because of what's in the pipe and the temperature, 352 meters per second. All right, so now we need to figure out which of these we're going to use. And the fact that they said that it's closed at one end really means that we're going to use the one with the word closed in it. All right, so I'm even going to just write that down. Fn closed is equal to n v over 4L. All right. So the fundamental is the first fundamental. It's that first standing wave. We could have asked for the second fundamental, the third. I should have probably written the question of what's the first fundamental frequency. I'll probably even change that here. So really, yeah, we're using a closed one, so we just need to plug in what we know. All right, so in fact, we're not even going to go with n. Let's see how well I can erase. That might be too small. Let's go with there. We're not looking for Fn. We're looking for F1. Okay. So that means we can just go, so F1 closed is equal to 1. I didn't even have to write that down there. Wave speed, they told us, was 352 meters per second over 4 times the L, they said, was 0.2 meters. I can already do a little bit of, let's not do that. All right, so let's just type that in. I don't need to care about the 1. So bring out the trusty calculator. So 352 divided by, parentheses, 4 times 0.2 equals 440. Now for our unit here, so F, I messed up before, so hopefully you watched until this point. This F, we could have put the frequency of the fundamental to know, like we're talking about hertz here. The other way we can kind of know it is our meters are going to cancel out here. So our unit is kind of 1 over seconds. And that is pretty much what a hertz is. So yeah, so the frequency of this pipe, the first fundamental frequency of this pipe is 440 hertz. The thing about fundamentals, though, is you can have multiple fundamentals going on at the same time. And it's how the fundamentals interact with each other that kind of lets different instruments sound different. It's not just about pitch or loudness. It's also about these fundamentals. And if remember right, essentially this kind of goes into why like string instruments sound different than brass, and brass sounds different than woodwind. It's all about how many fundamentals are there and what frequencies do they occur at. All right, so I'm going to leave it there. Good luck.